Okay. Good morning, Dean Nabante. Good morning, classmate. So my report is about the t-test, then the normal distribution and probability. Okay. First, let's discuss what is t-test and its different types of t-test. Okay. So what is t-test? A t-test, also known as student t-test, it is a tool for evaluating the means of one or two populations using hypothesis testing. A t-test may be used to evaluate whether a single group differs from a known value. This one refers to one sample t-test. Then whether two groups differ from each other, this one refers to independent two sample t-test, or whether there is a significant difference in paired measurement. This one refers to a paired or dependent sample t-test. Okay, how are t-tests used? First, you define the hypothesis you are going to test and specify the acceptable list of drawing a faulty conclusion. For example, when comparing two populations, you might hypothesize that their means are the same and you decide on an acceptable probability of concluding that the difference exists when that is not true. Next, you calculate a test statistic from your data and compare it to a theoretical value from a t distribution. Depending on the outcome, you either reject or fail to reject your null hypothesis. Okay. What if I have more than two groups? You cannot use a t-test. Instead, use a multiple comparison method. Example are analysis of variance or ANOVA, Turkey-Kramer pairwise comparison, Dunnett's comparison to a control, and analysis of means or ANOVA. Okay. T-test assumptions. While t-tests are relatively robust to deviation from assumption, t-tests do assume that the data are continuous, the sample data have been randomly sampled from a population, then there is homogeneity of variance, example, the variability of the data in each group is similar, then the distribution is approximately normal. The two sample t-tests, we must have independent samples. If the samples are not independent, then a paired t-test may be appropriate. Okay, so we have types of t-tests. So there are three types of t-tests to compare means. Okay, I have one sample t-test, a two sample t-test, and a paired t-test. The table on the next slide will summarize the characteristics of each and provide guidance on how to choose the correct test. Okay, so this is the the table that would summarize the three types of t-test: the one sample t-test, the two sample t-test, and the paired t-test. Okay, one sample t-test, it is also known as student t-test, while two sample t-test, this one also known as independent group t-test, independent sample t-test, okay, equal variances t-test, pooled t-test, unequal variances t-test. So the two sample t-test is the synonyms are this are the following. Okay. Then the paired t-test po, also known as paired group t-test or dependent sample t-test. Okay, as to numbers of variables, for one sample t-test, one variable. For the two sample t-test, we have two variables. Then for paired t-test, we have also two variables. Type of variable. For one sample t-test, we have continuous measurement. For two sample t-tests, we have continuous measurement and, categorical or nominal to define groups. Okay. For paired t-test, we have continuous measurement. Okay, it should be continuous measurement and categorical or nominal to define pairing within group. Okay. As to the purpose of the test, okay, the purpose of one sample t-test is to decide if the population mean is equal to a specific value or not. Then the purpose of two sample t-tests decide if the population mean for two different groups are equal or not. Then for the purpose of paired t-test is to decide if the difference between paired measurements for a population is zero or not. Okay, example of one sample t-test. Mean heart rate of a group of people is equal to 65 or not. So example of one sample t-test. Okay. Then example of two sample t-tests is this one. Mean heart rates for two groups of people are the same or not. Okay. Then the example of paired t-test, mean difference in heart rate for a group of people before and after exercise is zero or not. Okay. Then estimate of population mean, one sample t-test, sample average. For two sample t-tests, sample average of each group. Then for the paired t-test, sample average of the differences in paired measurement. Okay. Then population standard deviation. For one sample t-test, unknown, use sample standard deviation. If unknown, use sample standard deviation. Two sample t-tests, unknown, use sample standard deviation for each group. Then for paired t-test, unknown, use sample standard deviation of differences in paired measurements. Okay. Degrees of freedom. Okay. For one sample t-test, number of observation in sample minus 1. So n minus 1 or the sample minus 1. For two sample t-tests, okay, sum of or observation in each sample minus 1. So sample, okay, sample of each group. Okay, so sample of the first group, okay, then sample the second group minus 2, sorry, minus 2. So this is the degree of freedom. Then for paired t-test, number of paired observation in sample minus 1. So simply the same with one sample t-test, n minus 1, okay, sample minus 1. So we need this because later on, if we will going to perform the following t-test, one sample, two sample, or paired t-test, we will use the degrees of freedom or degree of freedom. Okay, one-tailed or two-tailed test. Okay, when you define the hypothesis, you also define whether you have a one-tailed or two-tailed test. You should make decision before collecting your data or doing any calculation. You have this decision for all three of the tests for means. To explain, let us use the one sample t-test. Suppose we have a random sample of protein bars and the label for the bars advertises 20 grams of protein per bar. The null hypothesis is that the unknown population mean is 20. Suppose we simply want to know if the data shows we have a different population mean. In this situation, we will have this hypothesis, okay? This would be our hypothesis, okay? So here we have two-tailed tests. We will use the data to see if the sample average differ sufficiently from 20, either higher or lower, to conclude that the unknown population mean is different from 20. Okay? Then suppose that we want to know whether the advertising on the label is correct. Does the data support the idea that the unknown population mean is at least 20 or not? In this situation, our hypotheses are we have a one-tailed t-test, a one-tailed test. We will use the data to see if the sample average is sufficiently less than 20, okay, less than 20 to reject the hypothesis that the unknown population mean is 20 or higher. Okay, see the tail for hypothesis test. Okay, so um, see the tail for the hypothesis test section, t-distribution page for images that illustrate concept for one-tailed and two-tailed tests. Now, how to perform a t-test? Okay, for all the t-tests involving means, you perform the same step in analysis. Okay, first step is define your null and alternative hypothesis before collecting your data. Decide on the alpha value. Okay, this is the alpha value. This involves determining the risk you are willing to take of drawing the wrong conclusion. Okay, for example, suppose you set the alpha value to 0.05 when comparing two independent groups. Here, you have decided on a 5% risk of concluding the unknown population mean are different when they are not. Okay? Then three, check the data for errors. Then four, next step, check the assumption for the test. Then fifth step is perform the test and draw your conclusion. All t-test means involve calculating the test statistic. You compare the test statistic to a theoretical value from the distribution. Okay? The theoretical value involves both the alpha value and the degree of freedom for your data. Okay? Then we will discuss next the how to perform the one sample t-test, two sample t-test, and the pair t-test. Okay. Now, the one sample t-test, um, it is a statistical hypothesis test used to determine whether an unknown population mean is different from a specific value. Okay. When we can use the one sample t-test? We can use the test for continuous data. Your data should be random sample from a normal population. Okay. What if my data isn't clearly normally distributed? Okay. If your sample sizes are very small, you might not be able to test for normality. You might need to rely on your understanding of the data. When you cannot safely assume normality, you can perform non-parametric tests that doesn't assume normality. Okay, using one sample t-test, what do we need? Okay, for the one sample t-test, we need one variable. Okay, we also have an idea or a hypothesis that the mean of the population has some value. Here are some examples. Okay, so these are the example of or a situation wherein we will use um one sample t-test. Okay, a hospital has a random sample of cholesterol measurements for men. These patients were seen for issue other than cholesterol. Okay, they were not taking any medication for high cholesterol. The hospital wants to know if the unknown mean cholesterol for patients is different from a goal level of 200 milligrams. We measure okay, so this is an example of a situation wherein we can use one sample t-test. The second example is this one. We measure the gram of protein for a sample of energy bars. The label claims that the bar have 20 gram of protein. We want to know if the labels are correct or not. Okay, so one sample t-test assumes that for a valid test, we need data value that are independent, okay, meaning values are not related to one another. Then it should be continuous, okay, obtained via a simple random sample from a population. Okay, also the population is assumed to be normally distributed. Okay, so um, example of one sample t-test. Imagine we have collected a random sample of 31 energy bars from a number of different what's this, stores to represent the population of energy bars to the general consumer. The label on the bars claim that each bar contains 20 grams of protein. So we collected 31 energy bars. Okay. Then the labels on the bar claim that each bar contains 20 grams of protein. Okay, so this is the table, okay, of the grams of protein of the 31 energy bars from different stores. Okay, from different stores. So if you look at the table here, you see that some bars have less than 20 grams of protein. So you will see some bars, energy bars, they have what? Less than 20 gram of protein, like this one, 19.72. Okay, 19.57, 18.28. So there are protein energy bars that have less than 20 grams of protein. Then other bars have more than 20 grams of protein, like this one, 24, 21.08, 22.40. Okay, you might think that the data support the idea that the labels are correct. Others might disagree. The statistical test provides a sound method to make a decision so that everyone makes the same decision on the same set of data values. Okay, so checking the data, let's start by answering. Is the T-test an appropriate method to test the energy bars have 20 grams of protein? The list below check the requirements for the test. So we will check whether it is appropriate to use the one sample T-test for this situation. So the data values are independent. Okay, the values are independent. The gram of protein in one energy bar do not depend on the gram in any other energy bar. So it is independent. The values are independent. An example of dependent value would be if you collected energy bars from a single production lot. Okay, a sample from a single lot is representative of that lot, not energy bars in general. Okay, so this one, uh, it is an example of dependent values. Okay. Then the data value are grams of protein. The measurement are continuous. Okay. We assume the energy bars are a simple random sample from the population of the energy bars available to the general consumer. Okay. Then the last one, we assume the population from which we are collecting our sample is normally distributed. And for a large sample, we can check this assumption. We decide that t-test is an appropriate method. Okay. Before jumping into analysis, we should take a quick look at the data here. Okay. Okay. So we have a table here shows the histogram and summary statistic for the energy bars. Okay. So we have the summary statistics here. From a quick look at the histogram, we see that there are no unusual points or outliers. Okay, the data look roughly bell-shaped, so our assumption of our normal distribution seemed reasonable. So it is correct to assume that we have a normal distribution. Okay, from a quick look at the statistics, we see that the average is 21.4. So we have here, okay, 21.4T. This one, the mean, the average, the no, this is the average of 21.4T, and about which is about 20. Thus, this average from our sample of 31 bars invalidate the label's claim of 20 grams of protein for the unknown entire population mean or not. Okay. So we will perform the one sample t-test. Okay. For the t-test calculation, we need the average, standard deviation, and sample size. Wherein we can see that in the summary of statistics here. Okay. So these are shown in the summary of statistics. Okay. The 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 average, the standard deviation, and the sample size. Okay, we round the statistics to two decimal places. Okay, okay, okay. So we start by finding the difference between the sample average and 20. Okay, so in here, okay, so we will get the difference between the sample and the 20. So here, our sample, okay, the 21.40 minus 20, okay, so we have 1.4, okay. Next, we calculate the standard error for the mean. So the calculation for the standard error for the mean is this one, okay, square root of the square root of the sample, which is 31. Then here, this one is the 2.54, the standard deviation, 2.5 or 2.54, this one, okay. So we do the operation, so we will get 0.456 or 0.456, okay. So this matches the value in our table here, okay, this one. Okay. Now we have the pieces for our test statistics. So we calculate our test statistics as, okay, difference over standard error. So the 1.4 here, okay, then divided by 2.0456, okay, the standard error for the mean, then we will get the 3.07. Okay. Now, to make our decision, we compared the test statistics to a value from the t distribution. Okay. Okay. So this activity involves four steps. Okay. The first step is we calculate a statistic. We calculate a test statistics. So our test statistics is 3.01. This is our test statistics 3.0. Sorry, 3.07. Okay. Next step is we decide on the risk we are willing to take for declaring a difference when there is not a difference. Okay. So for the energy bar data, we decide that we are willing to take 5% risk of saying that the unknown population mean is different from 20 when in fact it is not. So in statistics speak, we set the alpha value to 0.05, okay, the 5%, 0.05. In practice, setting your risk level, okay, should be made before collecting the data. So we should decide what would be our risk level before we will collect the data. Okay, the third step is we need to find the value from the t distribution based on our decision. For a t-test, we need the degree of freedom to find the value. Okay, so this is the equation that we saw sa table natin comparing the three types of t-test. Okay, the equation for the degree of freedom. So we have here the sample size minus 1. Okay, the sample size is 31 minus 1. So 30. 30 is our degree of freedom. Okay, so the critical value of t with the alpha value of 0.05, okay, from here, the uh, the what's this? The value that we are willing to take. Okay, that risk value that we are willing to take. Okay, the 0.05 and the 30, which is the degree of freedom. Okay, so it's the positive negative of 2.043. So most statistics books have lookup tables for the distribution. You can also find tables online. Okay, so for the we can most statistics books have a lookup tables for the distribution. So we can uh, for this one we can use a table and we can search it that online. Most likely situation is that you will use software or will not use printed tables. Okay, so we compare the value of our statistics, okay, 3.07 to the t-value. Okay, so where did we get this 3.07? So 3.07 is our test statistics, okay? Then um, we will compare that to our hypothesis, which is 2.043. So since our test statistics is greater than 2.043, we can say that we can reject the null hypothesis that the mean gram of protein is equal to 20. So we can reject our null hypothesis that the mean gram of protein is equal to 20. Okay, is equal to 20. We make a practical conclusion that the labels are incorrect and the population mean gram of protein is greater than 20. Okay, greater than 20. So we already uh, can decide based on our um, test statistics and comparing it to our hypothesis. Okay. Next type of t-test is the two-sample t-test. So what is two-sample t-test? Okay. It is known as independent sample t-test. It is a method used to test whether the unknown population mean of two groups are equal or not. Okay. In this, is this the same as the A/B test? Okay, yes. Two-sample t-test is used to analyze the result from A/B test. Okay, we can use where when we can use the this test. Okay, we can use this test when our data values are independent, okay, randomly sampled from two normal population, and the two independent groups have equal variances. Okay, so these are the conditions wherein we can use the two sample t-test. Okay, what if I have more than two groups? Okay, use a multiple comparison method like analysis of variance ANOVA is one such method. Other multiple comparison methods include the Turkey-Kramer test of all pairwise differences, analysis of mean anom to compare group mean to the overall mean, or Donnett's test to compare each group mean to a control mean. Okay? Then what if the variances for my two groups are not equal? So we can still use the two sample t-test. Um, you use a different estimate of the standard deviation. So if ever um, our variances from our two groups are not equal, yes, we can still use the sample t-test. Then we can use the different estimate of the standard deviation. Okay. What if my data isn't nearly normally distributed? Okay. If our sample size are very small, you might not able to test for normality or for its normality. We might need to rely on our understanding of the data. When you cannot safely assume normality, you can perform a non-parametric test that doesn't assume normality. Okay. So using the two sample t-test, what do we need? So um, for two sample t-test, we need two variables. Okay, one variable define the groups. The second variable is the measurement of the interest. Okay, we also have an idea or hypothesis that the means of the underlying population of the two groups are different. Okay, so we have examples here. The first one, we have a student who speak English as their first language and the student who do not. All students take a reading test. Our two groups are the native English speaker, okay, and the non-native speaker. So we have two groups, the native speakers and non-native speaker. Our measurement are the test score. Okay, our idea is that the mean test score for the underlying population of native and non-native English speakers are not the same. We want to know if the mean score for population of native English speaker is different from the people who learn English as their second language. Okay, so if we have this kind of situation, okay, uh, we can use the two sample tests. Okay. Second situation wherein we can use two sample tests is this one. We measure the gram of protein in two different brands, okay, of energy bars. Our two groups are the two brands, okay? The two groups are the two brands of the energy bars. Okay. Our measurement is the gram of protein for each energy bar. Our idea is that the mean gram of protein for the underlying population for the two brands may be different. We want to know if we have evidence that the mean gram of protein for the two brands of the energy bars is different or not. Okay, so for this situation, we can use sample t-test. Okay, to conduct a valid test, okay, data value must be independent. So these are the characteristics of situation or uh, the situation wherein we can use this the two sample t-test. Okay, the data values must be independent. Okay, measurement for one observation do not affect measurement for any other observation. So it's the independent. Data in each group must be obtained by a random sample from the population. Okay. Data in each group are normally distributed. Okay. Then the data are continuous. Okay. Then the variances for the two independent groups are equal. Okay. Groups are equal. For very small groups of data, it can be hard to test this requirement. Below, we will discuss, or on the next power slide, we will discuss how to check the requirement using a software and what to do when a requirement isn't met. Okay. Okay. So this one, I'm referring to this one, the requirement checking of data. Okay. Example of a two sample test here. Let me remove this. Okay. One way to measure a person's fitness is to measure their body fat percentage. Okay. Average body fat percentages vary by age, but according to some guidelines, the normal range for men is 15 to 20% body fat, and the normal range for women is 20 to 25% body fat. Okay. Our sample data is from a group of men and women who did work out at a gym 3 times a week for a year. Then their trainer measured their body fat. Okay, so we can see the table here. Okay, containing the data. Okay, containing the data. So group of men and women and their body fat percentages. Okay. You can clearly see at the table here, okay, that some overlap in the body fat measurement for the men and women in our sample, but also some differences. Okay, just by looking at the data, it's hard to draw any solid conclusion about whether the underlying population of men and women, okay, at the gym have the same mean body fat. This is the value of statistics test. They provide a common, statistically valid way to make a decision so that everyone makes the same decision on the same set of data values. Okay, so let's check the data. Let's start by answering, is the two sample t-test an appropriate method to evaluate the difference in body fat between men and women? Okay. So the data values are independent. So because the body fat for any one person does not depend on the body fat for another person. So it is dependent. We assume that people measured represent a simple random sample from the population of the members of the gym. Okay? We assume the data are normally distributed and we can check this assumption. Then the data values are body fats measurement. The measurement are continuous. So we have our data is continuous. We assume that the variances for men and women are equal, and we can check this assumption. Okay. So before jumping into analysis, we should always take a look at the data first. Okay. So the figure below shows the histogram and summary of statistics for men and women. So this is a summary statistics for the body fat percentage for the group of women, and the table here summary statistics for the body fat percentage of the group of men. Okay, so we need this information for us to run or to perform the two sample t-tests. Okay, the two histograms are on the same scale. From a quick look, we can see, okay, we can see that there are no very unusual points or outliers. The data look roughly bell-shaped. Okay, so our initial idea of a normal distribution seems reasonable. Examining the summary statistics, we see that the standard deviation are similar. This supports the idea of equal variances. We can also check this using a test of variances. Based on this observation, um, the two sample test appears to be an appropriate method to test for a difference in mean, okay, for this situation or for this example. Okay. Okay, how to perform, okay, the two sample t-test. So let's try to perform the two sample t-test. Okay, for each group, we need the average. Same thing with the first type with the sample uh, one sample t-test. Okay, so we need the average, the standard deviation, and the sample size. These are shown in the table here. Okay. Okay, so we have the uh, the data or the information, the figure for the average, standard deviation, and sample size. The sample size, standard deviation, and um, the average. Okay. Without doing any testing, we can see from here, from this table, that the averages for men and women in our samples are not the same. Okay. So the averages, okay, it's not the same. Okay, but how different are they? Are the averages close enough for us to conclude that the mean body fat is the same for the larger population of men and women at the gym? Or are the averages too different for us to make this conclusion? Okay, to make this conclusion. So we will further explain the principles underlying two sample t-tests in the statistical details section, okay, section below. But let's first proceed through the steps from beginning to end. We start by calculating our test statistics. Okay, this calculation begin with the finding the difference between two averages. Okay, so first we need to find the difference between the two averages. So 22 here, 22.29 minus 14.95. We just did uh, subtracted it to get the difference of the two averages. So 22.29, this one, the average for group of the women. Then the 14.95, the average of men. So 22.29 minus 14.95, so we have 7.34. Okay, this difference in our samples estimate the difference between the population mean of the two groups. Okay, so we have 7.34. Okay, next we calculate the full standard deviation. This builds a combined estimate of the overall standard deviation. The estimate adjusts for the different group size. First, we calculate the full variance. So this is the formula for the full variance. Okay, so this one is the sample, okay, of the I think this is the men group. Let's see. The first one, the women group. Okay, so this sample size of the woman is 10. The sample size of men is 13. So this one, 10. Then this one is the sample size of women. This is sample size of men. Uh, minus one, and this one is the standard deviation. Okay, 5.32, 6.84. Okay, 5.32, 6.84. Okay, over then the sample size of women plus the sample size of men minus 2. So we just do the mathematical operation here. Okay, then we will get, okay, 38.88. So this is our pooled variance. Okay. Okay. Then, since we have this figure 38.88, our pooled variance, we take the square root of the pooled variance to get the pooled standard deviation. Okay, so we will, to get the standard deviation, we need to get the square root of the pooled variance. So the square root of 38.88 is 6.24. So this is our pooled standard deviation. Now we now have all the pieces of for our test statistics. Okay, so we have the difference of the averages, the pooled standard deviation, and the sample size. So we will just um, uh, do this equation to perform the two sample t-test. Okay, so difference of the group average over standard error of difference. So 7.34, where did we get this one? Is this one the average, that the difference between the two averages? 17.34 over 6.24. Okay, then 1 over 10 plus 1 over 13. I think this is the sample size of women. Then this one is the sample size of men. Okay, so we have 17.34 over 2.62. So we have 2.80 or 2.80. So to evaluate the difference between the mean in order to make a decision about our gym program, we now compare the test statistics to theoretical value from the T distribution. Okay, this activity involves four steps. Okay, we decide on the risk. Again, we decide on the risk that we are willing to take for declaring the significance difference. For the body fat data, we decide that we are willing to take a 5% risk of saying that the unknown population mean for men and women are not equal when they really are. Okay, in statistics speak, the significance level denoted by, I think, alpha, okay, is set to 0.05, okay, which is this one is the 5%. It is a good practice to make this decision before collecting the data and before calculating the test statistics. Okay, next step, we calculate the test statistics. Our test statistics is 2.08. Okay, this one is our test statistics. We find our theoretical value from the T distribution based on our null hypothesis, which state that the mean for men and women are equal. Most statistics books, okay, they have tables for the T distribution. Okay, then we can also search for the table online. Okay, to find the value, we need the significance level. Okay, which is this one, yung 5%, but we converted it to the decimal, so 0.05. Then the degree of freedom, okay, that we, okay, the degree of freedom, okay. So based on the sample size of the two group for the body fat data, okay, since this one is two sample t-test. Okay, so this is the formula to have the degree of freedom. So sample of the first group, sample size of the second group, minus 2. So 10 plus 13 minus 2, we have 21. Okay? The t-value, okay, with the t-value with alpha value of 0.05 and 25 degree of freedom is 2.080. Okay, 2.080. Okay, we compare the value of our statistic, which is 2.8, to the t-value, okay, which is 2.080. Okay, so here we can say that our statistic value is greater than to the t-value. So what decision can we make here? We can reject the null hypothesis that the mean body fat for men and women are equal. And we can conclude that we have evidence that the body fat in the population is different between men and women. Now, let's move on the paired t-test. What is the paired t-test? The paired t-test is a method used to test whether the mean difference between pairs of measurements is zero or not. Okay? So when can we use this test? Okay, when we can use paired t-test? We can use the test when our data value are paired measurement. For example, you might have before and after measurement for a group of people. Also, the distribution of differences between a paired measurement should be normally distributed. Okay? What are some other names for the paired t-test? So, we already mentioned this one dun sa ating table kanina, comparison of the three types of t-test. So, paired t-test, also known as the dependent sample t-test, paired difference t-test, match pairs t-test, and repeated sample t-test. Okay. So, if ever you encounter this word or names, they are also referring to paired t-test. What if my data isn't nearly normally distributed? So what are we going to do if our data is not nearly normally distributed? Okay. If your sample size are very small, you might not be able to test for normality. You might need to rely on our understanding of data, or you can perform non-parametric tests that doesn't assume normality. Okay. Using the paired t-test, okay? So, what do we need? Okay. First, for paired t-test, we need two variables. Okay. One variable defines the pairs for the observation. The second variable is a measurement. Sometimes we already have the paired difference for the measurement variable. Other times we have separate variables for before and after measurement for each pair and need to calculate the differences. Okay. We also have an idea or hypothesis that the difference between pairs is zero. So this is an example of a situation wherein we can use paired t-test. Okay. First, a group of people with dry skin use a medicated lotion on one arm and non-medicated lotion on their other arm. After a week, a doctor measures their redness on each arm. We want to know if the medicated lotion is better than the non-medicated lotion. We do this by finding out if the arm with medicated lotion has less redness than the other arm. Since we have pairs for measurement for each person, we find differences. We test if the mean difference is zero or not. Okay. Then another example, we measure weights of people in a program to quit smoking. Okay, each person or individual, we have the weight at the start and the end of the program. We want to know if the mean weight change for people in the program is zero or not. Okay, then another example wherein we can use paired t-test is this one. An instructor gives student an exam and the next day gives student a different exam on the same material. The instructor wants to know if the two exams, okay, are equally difficult. So we calculate the difference in exam score for each student. So we test if the mean difference is zero or not. Okay. To apply the paired t-test, okay, for differences between paired measurement, the following assumption need to hold. Okay, first, subject must be independent. Measurement for one subject do not affect the measurement for any other subject. Each of the paired measurement must be obtained from the same subject. For example, the before and after weight of the smoker in the example above must be from the same person. Okay? Then the measured differences are normally distributed. Okay. Okay. Paired t-test example. Okay. So an instructor wants to use two exam in her classes next year. This year, she gives both exam to the student. She wants to know if the exam are equally difficult and wants to check this by looking at the difference between scores. Okay, if the mean difference between scores for student is close enough to zero, she will make a practical conclusion that the exams are equally difficult. Okay, so we can have this data here. Okay, so the students here who uh and their scores for the first exam and their scores for the second exam, and the difference, okay, between the exam 1 and exam 2. So if you look at the table, you see some of the scores difference are positive and some are negative. You might think that the two exams are equally difficult. Okay, other people might disagree. The statistical test gives a common way to make decision so that everyone make the same decision on the same data. Okay, so checking the data. Let's check the data. Um, let's answer the following question. Is the paired t-test an appropriate method to, let's answer this question first. Okay, is the paired t-test an appropriate method to evaluate the difference in difficulty between the two exams? Okay, so subjects are independent. So uh, same requirement. Okay, the subjects must be independent, meaning each student does their own work on the two exam. Okay, each of the paired measurement are obtained from the same subject. Each student take both tests. Okay, the distribution of differences is normally distributed. Okay, for now we will assume this is true. We will test this later. We decide that we have selected a valid analysis method. Okay, so before jumping into analysis, we should plot the data. The table we have here in the figures shows the histogram and the summary statistics for the score differences. So we have the summary statistics here. From the histogram, we see that there are no very unusual points or outliers. The data are roughly bell-shaped, so our idea of a normal distribution for the differences seems reasonable. Okay, for the statistics, we see that the average or mean difference is 1.3. Okay, 1.3. Is this close enough to zero for the instructor to decide that the two exams are equally difficult or not? Okay, so how to perform the purity test? Okay, so this is the steps to perform the t-test. Well, further explain the principles underlying the paired t-test in statistical details. Okay, but let us proceed through the step from beginning to end. Okay, first start by calculating our test statistics. To accomplish this, we need the average, difference, the standard deviation of the difference, and the sample size. Okay, so we have here, okay, this one. So these are the statist statistics summary statistics. Okay, so the average 1.31, we have here this one, the mean. Then we have the standard error. Okay, 1.75, this one. Then in the formula above, n is the number of students or the sample, which is the number of the differences. Then the standard deviation of the differences is SD. Okay, standard deviation. Now, how we now have the pieces for our test statistics. So we will calculate our test statistics as this one. Average difference over standard error. So 1.31 over 1.75. So we have 0.750. Okay? To make a decision, our decision, we compare the test statistics to a value from the t distribution. Okay? First step, okay, we decide on the risk we are willing to take again for declaring the difference when there is not a difference. Okay? For the exam score data, we decide what are we willing to take. 5% risk of saying that the unknown mean exam score difference is zero when in reality it's not. Okay, the statistics speak, we set the significance level denote by A or alpha value, okay, A, alpha to 0.05. It is good practice, again, to make a decision before collecting the data and before calculating the calculating test statistics. Okay, next step, we calculate test statistics, which is uh, 0.750. So, ito po yun. Okay? So, third step, we find the value from the t distribution. Okay? So, to find this value, we need the significance level. Okay? 0.05 and the degree of freedom, and how to get this degrees of freedom. So, we have this formula or equation. Okay? This for this one is for the paired t-test. So the sample size minus 1, okay, the sample size is 10 minus 1, we have 15. So our degree of freedom is 15. So the value that we value with 0.05 and the 15 degree freedom, okay, the t value is 2.131. Now we will compare it. The next step, we will compare the value of our statistics, okay, the 0.750, okay, this one, okay, that's the statistics, then our t-value, which is 2.131. Okay, so we can see that 0.750 is less than 2.131. Okay, so we can now reject we can now reject the idea that the mean score difference is zero. We make the practical conclusion to consider exams are equally difficult. Okay? Are equally difficult. Since we rejected the idea that the mean score difference is zero. Okay? So we make the practical conclusion. We have our conclusion to consider exams are equally difficult. Okay? To make our decision, we compare the test statistics to a value from the t distribution. Okay? This activity involves the first step. Okay, naulit lang po siya. Okay. So we are done discussing the t-test and the three types of t-test, which are the um, one sample t-test, okay, then the two sample t-test and the paired t-test. Okay, so the second topic of my report is about um, normal the standard normal distribution and probability. So what is this all about? Okay, standard stand okay standard normal distribution. Okay, this one, normal distribution do not necessarily have the same mean and standard deviations. Each data set or distribution of score will have their own mean, standard deviation, and shape, even when they follow a normal distribution. Okay, a normal distribution with a mean of 0, okay, and standard deviation of 1 is known as standard normal distribution or a Z distribution. Okay, the standard normal distribution, okay, we can see that this one, okay, okay, is a mathematical or theoretical distribution that is frequently used by researchers to assess whether the distribution of the variables they are studying approximately follow a normal curve. So this one is the illustration of a standard normal distribution. Okay, every score in a normally distributed data set has an equivalent score in the standard normal distribution. This means that the standard normal distribution can be used to calculate the exact percentage of the scores between any 2 points or on the normal curve. Okay? Statisticians have workout tables for the standard normal curve that give the percentage of scores between any 2 points. In order to be able to use the table, score need to be converted into Z scores. So later we will try to convert scores, the raw scores to Z scores. Okay. So this is just an illustration of the standard normal distribution. Okay. Now, raw and Z scores. Okay. Raw scores are originally scores that are direct result of the measurement. However, they do not provide information about the position of that score in the distribution. Okay. Example of this is a score of 5 on an exam. Okay. This score does not indicate how well a student performed in relation to his or her classmate. So it's just a raw score, the 5. Okay. While Z-scores, also known as standard scores, are transformed raw scores and used to compare with the normal distribution. Okay? Z-scores describe the exact location of every score in a distribution. Example, um, whether the score is above or below the mean. Positive values indicate scores above the mean. Siyempre. Then the negative value indicates the score below the mean. Okay? So what the distance between the score and the mean in terms of the number of standard deviation? For example, a z-score of 1 is one standard deviation above the mean. So a z-score of negative 2.5 is two and a half standard deviation below the mean. So a z-score of 0 will represent the mean of distribution. Okay. So 0 will represent the mean of the distribution. Okay. Now, calculating z-score. Okay. A value from any normal distribution can be transformed into a corresponding value on a standard normal distribution using this formula. So we have a formula here wherein uh, for us to compute or calculate rather the z-score. Okay, where x, this one, is the standard value. Okay, standard value, okay, or the value on the standard distribution. Okay, x is the value of the original distribution. Okay, then this one, the mean of the original distribution. Okay, and the O here or the 0 is the standard deviation of the original distribution. Original distribution. Okay. To calculate a z-score, the mean and standard deviation are needed. So we need to insert the value or the figure of the mean and standard deviation. For example, if the mean of the normal distribution of the class test scores is 50 and the standard deviation is 10, to calculate the z-score for 26, the formula is applied. Okay? So here, the standardized value, where the standardized value or the value of the original distribution, okay, is 26. Then we have here the mean of the original distribution, we have 50. Okay, then over 10, okay, which is the uh standard deviation of the original value. Okay, so we do the mathematical operation. 26 minus 25. Okay, we have negative 24 over 10. Then we have negative 2.4. Okay, the z-score of the raw score of 26 in this given distribution is negative 2.4, meaning negative side means that the score is below the mean. Okay, the score is below the mean. Okay, transform your z-score back to a raw score. Additionally, a z-score can be transformed into a raw score by determining the deviation score by multiplying the z-score by standard deviation. Okay, we just need to multiply the z-score by the standard deviation, then determining the raw score by adding the mean to standard deviation. Okay, example of that, multiply z-score by standard deviation. Okay, so negative 2.4, okay, times 10, our standard deviation, the z-score, and the standard deviation, we have negative 0.24. And adding this deviation score to the mean. Okay, so negative 24 plus 50, we have 26. So we were able to transform a z-score back into the raw score. Okay. Now, um, standard normal curve table. Okay. The standard normal curve table is used to calculate the precise percentage of the score between the mean. Okay. Okay. So z-score of 0 and any other z-score. It can be used to determine, okay, the standard normal curve table. It can be used to determine the proportion of scores above or below the particular z-score. The proportion of the scores between the mean and a particular z-score, and the proportion of score between two z-score. Then the standard normal curve table is used by converting raw score to z-score, then finding the probabilities, and to determine the z-score for a particular proportion of score under the normal curve. Calculating the percentage of scores above or below the z-score. Summary of steps for determining percentage above or below the z-score. Convert the raw score to z-score if needed. Okay, so ayun na yung diniscuss natin kanina, how we will convert raw score to z-score. Draw a normal curve. Okay, draw a normal curve. Indicate where the z-score falls and the shade, the area you are trying to find. Use the table to find percentage to the left of the z-score. If we need to find percentage to the right of the z-score or between two z-score, we will have to do some extra calculation. Okay. So calculating percentage of score above or below the z-score. Okay. So my report ends here. So we were able to discuss somehow the characteristics of of the t-test, the three types of t-test, and what are the conditions, situations wherein we can apply or appropriately use the three types of t-test. Okay, then we were able to discuss um, the standard normal distribution and probability. Okay, so okay, thank you. I'm Rolando P. Cabral Jr. Okay, thank you po. How is to stop?